I'm Yan-Sung Feng, the chair of this session, and welcome to the session, the last session of the day, and it's information retrieval and document analysis. So the first talk will be the cross-culture transfer learning for tax classification, presented by Dor.
Thank you for the introduction. So I'm going to start with a quick question for all of us. Who of you, and please raise your hand if this reflects what you feel, ever worked on a machine learning task and after 4 hours, 1 day, 1 week, found yourself dead end with no task-specific label data set you can use? So I know this is something that happened to me, and I see many hands being raised here. So this happened to us 2 years ago on eBay when we worked on a specific task in a specific low-resource language. And we said, well, there's got to be a way to somehow get past this obstacle, let's say. And this is eBay. So we have purchase information, purchase data, and review data for people from a bunch of countries, age ranges, level of education, ethnicity, gender, and so on. And we just asked ourselves, you know what, there's have to be a way to somehow leverage these differences between groups of people in general to enable text classification without the need for expensive task-specific data sets. So to better understand this question and what the answer for this question is, we need to go back and understand some definitions from the social sciences. So culture was defined as the collective programming of the mind which distinguishes the members of one group of people from another. And then membership in a cultural group was defined as thinking and acting in a certain way, in the light of particular goals, values, pictures of the world. So if we combine these two definitions, we can quite reasonably get that texts composed by members of a specific cultural group are distinct from those composed by members of another. And this is something we all know. All of you who worked on style transfer, we already know this. But we take this one step ahead and we say that the widely available bilingual data sets that can be found in social media, in e-commerce sites, in knowledge bases like Wikipedia, can be used to counteract the low availability of task-specific data sets. And so we get back to the question, and the answer we have is yes, for sure. We can use these differences between people in order to enable text classification without the need for task-specific data. And this is what I want to show you all today, how we did. So let's talk about the method and how it is actually done. Essentially, the algorithm goes like this. We need two collections of documents denoted as C0 and C1 from languages L0 and L1 respectively. We need a transformation method denoted as T, which we'll explain in later slides what it does. And we need one or more binary text classification target data sets. These are the data sets for which we want to get predictions, but unfortunately we don't have the labeled data sets. And the predictions we denote as Y hat T. So the steps are quite straightforward. We start by transforming the two document collections into a shared space using the transformation T. We then train a classifier on top of these representations. We denote this as H, hypothesis. We then, let's say, embed or project the evaluation data sets into the same space using the same transformation T. And finally, this transfer step, we perform inference using the already trained classifier on the target data set. And again, the classifier doesn't see the evaluation data sets. It's not exposed to the labels. It's only trained on C0 and C1 transformed. So let's look at a concrete example and understand why this works. What you see here is the sarcasm detection example. So we all know sarcasm detection, and what it turns out from social sciences is that there have been many research and previous work that have showed that Japanese people tend to display behaviors that are much less sarcastic than American. And then if we take product review data from the American and Japanese marketplaces of Amazon, we pass it through the transformation to get the document representation, and then we train a classifier using distance supervision, which means that we assign label values according to the language of origin. So you get a classifier that seemingly tries to discover whether an input document is originating from Japanese or American English. But what it actually learns is to do sarcasm detection. And then if you take a data set for which you want to get sarcasm predictions, and you pass it through this framework, the transformation and classifier, it actually does a good job, the classifier, even though we have not seen even one sample from this sarcasm, the classifier does a good job even though it hasn't seen even one example from the sarcasm task. So similarly for formality classification is the task of classifying a document as either formal or informal, another style of writing. And social science tells us that Germans tend to display behaviors that are much formal than Americans. And then we take reviews from the American and German websites of eBay, and we pass them through this framework, and what we get at the end is a classifier that seemingly tries to distinguish German and American English documents, but actually the classifier does an amazing good job on doing formality classification, and again, without even seeing one label from the target data set. So let's talk about transformations. This is obviously the heart of it all, and most of the math and heavy lifting in the paper is devoted to this part, and I encourage you all to go to the paper and see details. But essentially, a good transformation, what it does, it carries the cross-cultural signal from the raw text into the classifier, whereas a poor transformation causes the classifier to focus, let's say, on superficial differences. So for example, if we would take all the documents from the German collection and project them to the zero vector, obviously the classifier during the training phase will have a very easy job to distinguish between German and non-German documents, and we would get something like accuracy 1. But the transfer would then fail miserably because it hadn't learned anything related to cultures or formality in this case. So another thing we need to address, and again, we don't have time for this, so I'll just point it out in one bullet, we have a lot of issues of controlling confounding variables in the text that we do by matching the distributions of text and rating values and so on between the two document collections, so that the classifier has, let's say, quote unquote, nothing else it can focus on rather than the cross-cultural difference itself. So if we look at these transformations and we open this black box, what we essentially see inside is a three-step process. First, translation, then word embeddings, and then document representation. So let's talk about translation. Essentially, we evaluated many different types of translations, namely what we call MT, state-of-the-art machine translation system, and NN for word-by-word nearest neighbor search. The simplest thing you can imagine, just take one word and replace it with its nearest neighbor from the other language using multilingual word embeddings. And these two choices represent a trade-off between complexity and accuracy, which will be interesting to see during the results section, what happens then when we employ these two methods. And then we have the word embedding, which is quite straightforward, and we end up with a variable length array of word vectors, which we want to somehow compress into a fixed length array. And you are all asking, what about deep learning? Why not BERT? Why not RNN? We'll see soon why not and why yes, okay? But what we did in this work, we tried to use two baselines. The first one is the unweighted word embedding average. Second one is called smooth inverse frequency by Aurora et al. From their ICLR 2017 work, which actually tends to what we all know from information retrieval 101, something like IDF, right? And we also propose our own document representation specifically designed for this case of bilingual training data meant to do inference or another third language, let's say. So let's derive this representation. Let's see how it works. So the work from 2017, as we just mentioned, proposes that text is composed by both local and global context. And they do a bunch of analysis and apply maximum likelihood estimation and obtain the same estimator we just saw a slide ago. So what we have in our case, we have, or we seek, more correctly, a document embedding to assist us to solve a binary classification task. More specifically, we assume that we have the conditional model for probability of each token given the class, given the language. So this is what we want to maximize, the expected low probability of a document. And then we have the two conditional models. We do a bunch of analysis, which I won't go into, but you can most certainly find in the paper. And eventually we get to this expression. And this expression can be seen as the bilingual extension of what we saw before. It's like the bilingual IDF. And if we look at the heat map that visualizes this function in R2, we can see that essentially words are assigned with a high weight in the document representation where they are rare in one or both of the language models, let's say, conditional language models. And this stands to reason because a word which is, let's say, rare in one collection and frequent in the other will have more discriminative power when used by the classifier to get decisions, to make decisions, excuse me. So to summarize, three representation methods as you see here, two baselines and our custom representation methods. So let's talk about the experiments and most importantly the results. First experiment considers the comparison between our approach which means to train on bilingual data alone and then evaluate on the target task, 0 labeled task-specific examples, in comparison to the same model that was trained solely on task-specific data. So these are the results. Everything here, by the way, is stratified 5-fold cross-validation experiment. You see AUC scores, and this is the task-specific results. This is our approach, and this is the AUC difference. And first of all, we see that the difference is negative, which is a good thing. This is a good sanity check. If we got that our approach, which does transfer learning, gets a better job than doing direct learning, we would need to stop and think if we are doing something which is, let's say, we have a leak or something like that. But essentially, the interesting thing is that our approach is 4% to 10% behind the models trained directly on task-specific data. And again, these is models that were trained with 0 task-specific examples, 100% examples from bilingual data sets. So the other type of analysis we want to do is the effect of the translation component. So again, we have the simple translation component and the state-of-the-art translation component, and the difference between them. And as you imagine, the better the translation is, the better the results are, which tends to reason because the translation is better able to convey the cross-cultural transfer, the cross-cultural signal from the raw data into the classifier. But what is interesting to see is that the impact has a great variety in it. It can be as high as 14% and as low as 0.3%. So this method works actually quite well in some cases, even when coupled with a low-quality translation method. Last dimension of evaluation here is the effect of the document representation. So we have 3 columns corresponding to the 3 methods we just saw. When language, the third one is our approach, the language-based approach. What we can see, first of all, is that unweighted methods are always behind the weighted methods, and also that our approach is generally the best, let's say. But the most interesting thing here, and I'll zoom into the 6 first rows of the table, is that the document representation and the translation scheme are complementary. What I mean by that, if we look only at the results from the setups where we use the machine translation, the state-of-the-art translation component, you can see that there is no statistical significance toward any approach, and that our approach, let's say, is less than 0.5% better than the others. On the other hand, if you look at the results for the setups where we used the simple translation component for doing the translation part, the results are extremely different, let's say. It can be up to 25 AUC points different. And this shows us something like that once the translation is of good quality, then you can compromise on the document representation. But once the translation of low quality, then a serious high-quality document representation is needed in order to extract as much of the cross-cultural signal as possible. So last thing to just show here is qualitative examples. So we employed the LIME algorithm by Ribeiro et al. From their 2016 work. And the LIME algorithm essentially assigns a weight to each word using local approximation that is, let's say, correlative to how much this word is a strong feature for the classification. And to the left, I think it's left, it's your left, yeah, my left also. To the left, you see 2 examples correctly classified as informal from one of the evaluation data sets, and to the right, you see 2 examples correctly classified as sarcastic from one of the evaluation data sets of sarcasm. So the interesting thing to see here is that our classifiers actually mark or highlight or take seriously, let's say, terms, words that actually cause a sentence or document to have informal or sarcastic meaning. For example, if we look at the left upper example, you see the word awesome, which actually what causes, let's say, the document of being informal. Or if we look at the upper right example, you'd see that the word amazing, the classifier understands that after this type of context, the word amazing kind of flips the meaning and causes it to be sarcastic. So it's interesting to see that the classifier is able to actually understand what we humans, let's say, think about these styles in text. And again, these and many other types of analysis can be found in the paper itself. So just to conclude what we have here, future work. First of all, additional text classification tasks, right? We talked about formality and sarcasm. What about politeness, emotion, romance, offense, humor, metaphor? So there are a bunch of things we can do here. This is only the beginning. This transfer learning framework can be, let's say, adapted to many other types of tasks and many other types of cross-cultural differences. And it will also be interesting not to apply it only on, let's say, different countries, but also differences in age, in gender, in line of occupation, and so on and so on. So another thing we want to do is to generalize to the multilingual case. Everything here was bilingual data set and a bilingual target task. What happens if you have 3, 4, 5 languages and you have, let's say, a multitask classification problem? So that is another area that we're interested in investigating. Another thing is the application beyond text classification. So maybe we found an additional, let's say, an entirely new source of data that we can use in NLP in general and not only in text classification. This is also an interesting line of work. And lastly, better transformation methods. So what we saw here is a 3-step, transformation method. And we all think about deep learning and pre-trained language models and so on. So we tried a bunch of these, and what we ended up getting when employing BERT and LASER and ELMO and QRNN and CNRNN and various other methods, we always got the same thing, is that the powerful model essentially overfits to the training data and does a horrible job at transferring the information and doing well on the target task. So it will be interesting in future work to see how we can leverage the knowledge and all we know about transformers and pre-trained language models in order to make these approaches even better. The main takeaways, and this is my last slide, just cross-cultural differences in bilingual data can be used and leveraged to do text classification without any task-specific data. And the performance can be close to those achieved by models directly trained on these data sets for those task-specific data sets. And lastly, document representation scheme that is specifically designed for the case of bilingual training data set can improve performance, especially when coupled with a low-quality translation scheme. So thank you all, and questions if you have, more than welcome.
Any questions? Any questions? No? No, I actually have a question for the results, the table of the results. So you have a NN, which is very naive kind of search space for the transformation. So you only use the nearest words from the one language to the another. So how that can be so good? Because that'll be as well as as better as the machine translation one, right?
Yeah. So first of all, I'd like to say that a bunch of this is, let's say, contributed to the pre-processing that was done. The matching between distributions of rating values and categories and so on has a huge effect here. If you just take, let's say, reviews from Amazon, throw them into BERT and see what happens, 100% accuracy, 0 transferabilities. So there has been a lot of engineering and a lot of work that has been done here in order to move aside any confounding factors so that these, let's say, translation method and document embedding method actually learn a useful representation that encapsulates the cross-cultural difference. So indeed, it looks naive, but there are a lot of engineering tricks behind this, let's say. I hope it answered the question.
Okay, yeah, I can understand. So one of the possible application will be to do the generation. Do you think is that possible to perform generation, text generation?
I think the generation is in style transfer. This is the direction they usually go for.
Yeah.
And
you can do the culture transfer.
Yeah, this is interesting. I think there are many things that can be done in this. This is, I think, let's say, just the start, and we can do a lot more of, let's say, harnessing bilingual data sets that are widely available online and can be used to do a bunch of things. Generation are obviously one of them. So yeah, that's a cool direction. Thank you.
Okay, thank you. Let's thank the speaker.